Well, I gave this lecture before for Seabourn, but each time I'm giving it, the Atlantic seems to be a little bit more wild. I think it's a celebration of the lecture. So at least I like to think it is. So, the Atlantic Ocean, and well, as many of you probably know, it's actually a surprisingly young ocean, and I'll talk a little bit more about that. But first of all, despite its young age, it is the second largest of the world's oceans, and it covers about 20% of the Earth's surface, and it hosts about 29% of the water surface area of the planet. And well, Jules Verne is very inspirational for geoscientists, although he always didn't, get it perfectly right. But Captain Nemo and his adventures under the ocean, 20,000 leagues under the sea, and I'll come back to this a little later. Well, he had an anticipation of all the treasures we find under the water, all the sea monsters, and of course all the volcanoes, as you see here. And I'll talk a little bit more in a modern sense about these features that we find in the Atlantic. This is a map of the Atlantic. Broadly speaking, it's divided into the north and southern part. Around about the equator, we make a distinction here. And as you see, there is this somewhat lighter colored area on the map that's called the Mid-Atlantic Ridge. And you find this on almost every globe. But what most people don't realize is this is a real mountain chain that's actually under the ocean. And we'll explore this a little bit more now. So, let's see. So here we are. This is Iceland up here, and here you see this mountain chain running like a spine down the Atlantic Ocean, and it has a lot of crisscrossing fractures and faults. And at the moment we are just about here in this area. Sorry, it's a bit hard to stay stable with this. And now we're going to look at the various features of the Atlantic. At least that's my intention. So the Atlantic Ocean is the second largest ocean, as I said, and it covers more than a quarter of the water surface of the Earth. Just to give you a flavor, the United States is less than a sixth of the size of the Atlantic Ocean in map view. And the Atlantic Ocean is very young. It only formed in the Jurassic period. This is when the dinosaurs went around. And the other oceans are all a lot older. So Jurassic was 180 to 150 million years. That's when the ocean started to form. And it started to form from the breakup of a supercontinent. The supercontinent Pangaea. Pangaea means all Earth. And this goes back to this gentleman, Alfred Wegener. He was a geographer who realized that you could fit several of these continents together like in a jigsaw puzzle. If you put South America next to Africa and move them together, they fit. And not only do the outlines fit, he also noted that several of the fossil groups fit. And this is what I'm showing here in the little diagram up there. We don't have to go into the details, but he realized that certain types of fossils, they go across these oceans. They can be found on either side of the Atlantic, and that meant they must have been connected at some point in the past. And he got a lot of criticism for that. People didn't want to believe this. He had no real mechanism to explain how continents would move. He called it continental drift. Today we call it plate tectonics. And by the time he actually died on expedition in Greenland. By the time he died, it was still not widely accepted. Only in the 1960s, when people realized that there's magnetic anomalies on the ocean floor that actually mark the changes of the ocean floor, did the theory get widely accepted. So, and here we see a little reconstruction in the central image of Pangaea, all the continents together back in the Jurassic era. And then on the right-hand side, we see a reconstruction through time. And here you see the opening of the Atlantic. It started in the south, and then it was like a zipper. It was unzipping towards the north, and then it spread in the north as well. So the ocean crust that formed as a result of the unzipping is a little older in the southern part of the Atlantic than it is in the northern part of the Atlantic. So, and there's various reconstructions out there today, and on the left-hand side I'm showing one for Pangaea and the fate of the broken up continent Pangaea, and in the right-hand image you see the age of the oceanic crust that forms from the spreading. As soon as continents spread, mantle is upwelling and produces new oceanic crust that has a different composition than the continents, so it stays underwater and it's not floating like continents. And today we still have continental drift. The continents are still moving. The Atlantic is still spreading, but very slowly. It's spreading with about 2 centimeters a year. To give you a sense, this is about the speed with which your fingernails grow. The Pacific is a bigger and somewhat older ocean, and the Pacific spreads much faster. It spreads at 7 to 8 centimeters a year. Again, I'll give you an analogy. This is about the speed with which your hair grows. So you get a sense for the different things. Now, the Atlantic is spreading, the Pacific is spreading, both are spreading, and that means at some point we're running out of space. They're competing with each other. And I'll talk a little bit about that, because the Earth, of course, has a solution for that. So here we have the idea of spreading oceans, and the spreading ridge, the mid-Atlantic ridge, is exactly where the spreading manifests itself. The mid-oceanic ridge, this is where a lot of submarine volcanoes are located, and they are pushing material up and to the side. And whenever new rocks form at these submarine volcanoes, they actually inherit a certain magnetic signal at the time of formation. And this is what we see here. So if new volcanic rocks form, we impose a magnetic signal, and different times have different magnetic signals, and therefore we get stripes, magnetic stripes on the ocean floor, and this allows us to work out the age of the ocean floor. And of course, those rocks that formed a long time ago, they tend to be further towards the margins, and those rocks that are forming later on or very young, they tend to be in the center, near the ridge, the spreading ridge. So this is how we think it works at the moment with the spreading ridges. But of course, when you break up a big continent like Pangaea, you have to think about how that works. Well, we have good analogies here. For example, in East Africa, we have a rift zone, a continental rift zone, as we call it, in East Africa. The continents are breaking up. And we have this in Europe as well. The Rhine and Rhone graben is the same. And once we push this continental rift further apart, the sea creeps in. And our analogy for that is the Red Sea right now, the Red Sea rift. And eventually, once the continents have been pushed apart for considerable time, we have a real ocean like the Atlantic Ocean. So in the top right, you can anticipate these stages that we see in the various settings on Earth. And we believe that if a continental rift continues unhindered, eventually it'll make a big ocean. So where do we see these oceanic rifts? Well, there's very few places you can go them unless you go with a submersible all the way down to the ocean floor. But there's one exception, and that is Iceland. So I'll talk a little bit about Iceland. I had the pleasure of going to Iceland with Seabourn this summer, and it was a spectacular experience. But this time of the year, it's not so nice up there. So here, so I recommend it for summer. That's what I'm really saying. So Iceland, what is going on in Iceland? Well, Iceland sits right on this mid-Atlantic ridge. And we see this large fracture zone going all the way through Iceland. Here on the right-hand image, you can really see that the Earth crust is breaking apart into slivers here. And in Iceland, you can actually hop from the American plate to the Eurasian plate, or well, stand on both if you're lucky. So, and this is what we see there. But why do we see this only in Iceland? Well, the answer is Iceland is a bit peculiar. Iceland is two things together. It's a geological bundle. It is an Atlantic ridge coupled with a plume like Hawaii. And we have this stationary mantle plume, a hotspot as some people call it, rising up from depth, and it happens to coincide with a ridge, and therefore it pushes Iceland above the ocean. and therefore we can see it. So we can actually walk in a mid-Atlantic ridge because there's an additional push from underneath the Iceland plume, and this allows us to look at this in a lot of detail. So I'm going to spend a few minutes now in Iceland just to give you an impression of how we get our ideas about the ocean floor, because Iceland has it above the surface. So here it is. So this is how the fracture zones in Iceland look like. And the mid-ocean rift system here is above sea level because of the extra push. And once we have fractures going down to the ocean, going onto towards the sea level, like in the bottom right here, then indeed the ocean creeps in, and you get the idea of how these things might look underwater. And very close to the coast, it looks like this. You can actually go bathe on the plate boundary between North America and Eurasia, and you can even dive down there. So this is still very shallow. It's just a few tenths of meters, and there you can go there. You really see the fractures in the earth crust, and you can dive down there. I've never done this myself. These are images I got from a friend, but apparently it's quite exciting. So the average depth of the Atlantic Ocean is about 3,300 meters, and it reaches its deepest point in the Puerto Rico, and there we usually have a somewhat elevated water depth at the mid-Atlantic ridge. So when we look at this map here, sorry, we're up here. Iceland is just about here where the arrow is. So it's just off the map here. Here's the UK on the right. So if we look all the way down, the deepest parts of the Atlantic are actually in the margins. So I just told you the deepest area is here. But in the center at the ridge, we actually have an elevation. And the little cartoon in the bottom left shows you this elevation. There is actually, as I said, a mountain chain. And the mountain chain is heavily fractured. It comes down north to south, but also it has these perpendicular fractures that cut across the ridge. We call them transform faults. And when I was a young PhD student, I had the pleasure to sail on a few research ships, and here's a few of them, the Meteor and the Poseidon. And just to make you feel a little better, I put some of the bad weather shots in the top right. So I tell you, the Sojourn is a lovely ship, even in bad weather. These research ships are not quite built in the same way. So, and with these you can actually dredge rocks from the ocean floor. Dredge means you have these large steel buckets and they're thrown overboard and they are scraping rocks from the ocean floor, and then they're pulled up and you get actually samples from there. There's usually also submersibles, but they're very expensive, so people don't like to use them too frequently. But in certain kind of areas, this works rather well. But imagine the stress as a scientist if you are responsible for one of those dredges or one of those submersibles. You're sitting there at this computer screen, you're worried that this thing might come back, and I've seen some of them being lost, some of the dredges. The financial burden is enormous, and the mood on the ship is really bad for a few days afterwards, I tell you. So, but luckily, we can retrieve a lot of samples, and we can work with them. So this is where we get a pretty good idea. And as I said, we have a lot of this fissure volcanism that happens underwater. And this is an image of the Iceland eruption just from last year. And at the very initial stage of the Iceland eruption, you can actually see the fissure here. So let me just zoom in here a little bit. So see that this is a fracture that opened up, and this fracture is feeding lava to the surface. And underwater, the lava fountains are not as spectacular because there's a lot of water pressure, but the fractures are almost identical. We have these fractures and lava is oozing out along those fractures. So we have a magma reservoir that sits under the ocean ridge, and it's actually a very elongate magma reservoir. We like to think it's kind of cigar-shaped and then slightly offset, followed by another cigar. And this way we have likely magma under most of the ocean ridges of the world. And we have about 60,000 kilometers of ocean ridges. all over the globe, not just in the Atlantic, so there's a lot of magma. In fact, 85% of volcanism on this planet is submarine. We don't see it. What we see is only a tiny fraction at the surface. So here, this is how it manifests itself, and here we have a little bit of magma or lava tube forming, and there's a submersible observing this. That's the technical things in the bottom of the image, and very close to them we have these black and white smokers. I'll talk a little bit more about them. Of course, this is not smoke. This is actually minerals that precipitate from hot solutions that are expelled from the ocean crust. So when the hot solutions come out, then they meet the cold ocean water, and then there is a chemical reaction that leads to mineral precipitation. But I'll talk a little bit more about this towards the end. So here's a lot of impressions from how it looks underneath our feet. And there we have what we call pillow lavas. These are, well, pillow-shaped lava portions. And then we have also ropey lava and lava flows, as we've seen in the Canaries, in fact. The pillows form because lava often quenches against the cold ocean water, and then we continue the flow inside these tubes, and therefore they stay a little hotter inside than on the outside, and that actually insulates the lava, so we get these pillow features rather frequently. Here's a few more impressions of pillow lavas on the ocean floor. Every now and then they break out and they form little lava tongues, as for example in the bottom right-hand side. And this is a very characteristic feature, these pillows, that every geology student learns rather swiftly. If you see lavas like this, you know they formed underwater. So here's a few more impressions, and there is actually the arm of one of these submersibles that is taking a sample here. It's quite a sophisticated procedure to operate the arm and get the sample and retrieve the sample. So these are horribly expensive rocks by the time they enter the laboratories of this world, of our kind of universities and research centers. And yes, it's just a lump of volcanic rock. Technically, it has no value, but the amount of effort and resources that went in to retrieve them is quite spectacular. So here's a few more impressions and a few more of these pillow lavas. And of course, once there's no new eruptions, all sorts of life starts to take shape and form. And here, for example, we have various types of mollusks, shells, and mussels that start to colonize the areas. And with time, of course, there will be sediment on top as well, and eventually there is life on the ocean floor that recolonizes all these fresh volcanic rocks. Every now and then we find something spectacular. When the first submersibles went down into the ridge crest, they found these strange pillars and the roof over the pillars. And this was really puzzling for some time, but then we observed a submarine eruption, and this phenomenon is a bit like lava tubes. So we have lava that is expelled in the graben, in the depression on the ridge, and sometimes the lava drains out, but certain pillars may remain, particularly when we had some water involved, and then we actually get these hollow areas, and sooner or later they collapse. And the specimen I'm showing on the bottom right is actually from the bottom. It's not the surface, it's looking from underneath, and you see how these roof crusts were pushed up, and that the lava that was still liquid was getting thinner and thinner and being stretched out. So this is a wonderful specimen explaining the process of how these empty spaces can form even at the ocean floor. But they are metastable. Sooner or later, they will usually collapse. So I talked about smokers before that are actually not smoking. They are expelling hot liquids, and they build these chimneys. And this is a rather bizarre landscape, and I'll come back to this a little later, because these chimneys are actually very, very useful for resources, and they bring a lot of metals up from the ocean floor, but they are also the places of very simple, primitive bacteria living there. So a lot of what we call archaeobacteria, these actually single-celled organisms, they're not really bacteria, they just have the name bacteria for a lack of better understanding at the time when they were discovered. They live in these hot spring environments on the ocean floor. And there is speculation that they could have even been the place where life originated. So here's a few impressions, and there is an artist's drawing of how some of these single-celled archaeobacteria might actually look like, and they start to, well, enjoy the time there. They like the heat, they like the strange pH conditions. It's very acidic there, and they're really well adapted to these conditions. These are environments we would not survive in, but life has found a way to thrive even in those places. So, having looked at the center of the Atlantic Ocean, I'd like to spend a few minutes on the margins as well, and then come back to plumes for a little second. Well, the margins of the Atlantic Ocean, they are rather passive. We call them passive margins because of that, because the ocean widens. There is no volcanism at the margins for most part, and we have these areas along, for example, the Norwegian coast, the Irish coast, the Portuguese coast, where not much happens. But we do actually get some instability. We get some landslides. And the most famous landslide here is actually off the coast of Norway, the Storegger slide. This is an unstable continental shelf, and approximately 6,000 years before our time, there was a big landslide, and it actually caused a tsunami. And you can see the tsunami deposits in many places in Scotland, in Scandinavia, in Norway in particular, and also in the Shetland Islands and places like this. Well, we don't really see it in Iceland, but this is because Iceland has active volcanism, so a chance that we find any tsunami deposits there is slim, because if there's new lava erupting, they will be covered. So, what else is there? Well, I told you earlier that the Pacific and the Atlantic, they're both expanding. And it's very hard to have two oceans expanding at the same time without taking anything away. The Pacific has a ring of fire. So a lot of the ocean crust that's forming in the Pacific is subducted again. It sinks back into the ocean. But the Atlantic is very young. And the Atlantic hasn't really developed this feature yet. You need a certain maturity, a certain age for this to happen. And there's one place in the Atlantic where it has started, and that's the Caribbean. Some of you might go to the Caribbean on the transatlantic journey, and here we have a little volcanic arc. This is actually where the plate, the Atlantic plate, is subducted again, and it sinks back into the earth at about 2 centimeters a year, and it forms a string of new volcanoes. There's Montserrat and Guadeloupe and Dominica and a few of those places. And that's a very explosive type of volcanism, very different to the standard Atlantic type of volcanism. So here I'll show you various maps of this island arc, as we refer to it. And on the right-hand side is a scientific assessment. You see the Atlantic plate being pushed underneath the Caribbean plate. And this is where we get a string of little volcanoes. So there is speculation that offshore of Portugal, which is where we are right now, there may be something like this happening very soon as well. Some people argue it could have even started already. We are not entirely sure, but sooner or later there will be more of those explosive volcanoes at the margins of the entire Atlantic. That will be the geological fate. Sooner or later we will have Mount St. Helens and Mount Baker and Mount Hood, or volcanoes like this at the margins of the Atlantic as well, in geological time, not quite tomorrow. So I'd like to talk a few words about where we've just been and plumes, and the Atlantic is littered with plumes, and here's a map on the right-hand side, and this is the upper red box on the left-hand map, and there we have the Azores, Madeira, Canaries, and the Cape Verdes. We have all these island groups that don't fit either the subduction model nor the mid-ocean ridge model. They happen to be somewhere randomly distributed. And here we need what people call the Hawaiian plume model. We need some anomalies that come up from the deep mantle, and they feed the volcanism in those little archipelagos. So let me bring you here to the Canaries. We talked about this before. I'm showing in yellow in the right-hand top map the magnetic anomalies, and it's a little small, I'm sorry for that, I apologize, but they're Jurassic in age, these magnetic anomalies, and you can see that the island cluster of the Canaries cuts across this. So they're not related. So this is a very different feature. And in the lower map, I'm actually showing you all the different plumes that we geologists believe exist. And here we have different plume tracks, and the Canary Islands are one of them. The Azores is another one, and the Cape Verde are there. And of course, in the Pacific, we have the type locality of Hawaii, and this is where we have stationary mantle plume anomalies and plates that move. And so like a Bunsen burner, we burn volcano holes into the plate. And I wanted you to come with me to the South Atlantic for a second as well. The lower red box in the left-hand map, that's actually the Whalefish Ridge, and this is a spectacular area. And here we have another chain of volcanoes, submarine, and they go into the southern part of Africa. And there's a tiny little volcanic island just on the ridge, not as big as Iceland, but the phenomenon is very similar. And it's marked here TDC. That's Tristan da Cunha, and that is likely where the plume is located. So we have these stationary deep-seated anomalies and the moving plate as shown here on the right, and here this Whalefish Ridge is a result of exactly this phenomena. Now, some people asked me about the Azores, so I put some slides into my talk this morning, making it a little longer, I'm afraid, but I felt I should explain the Azores as well. The Azores are very different. The Azores are also plume related, we can tell from the magma chemistry, but the Azores, they actually sit up here. And they sit in a very strange place because I marked here with yellow circles the North American plate, the African plate, and the Eurasian plate. And the Azores sit at what we call a triple junction. It's very earthquake rich, there's a lot of activity there, and the Azores sit right in that spot where the three plates meet. And in this lower image here, it's a little small maybe, but there you can just about see the triple junction where the arrow is now here. There it is. And this is where the Azores sit. And in this image here, this is all the earthquake recorded over the last decades, each earthquake being a little dot. The stronger the earthquakes, the darker the color, so the red is more intense, and you can really see the earthquakes show the plate boundary, the triple junctions between these three plate boundaries. And we discussed this earlier. We came up the coast here of Morocco. Here's the Atlas Mountains, a lot of earthquakes there, a small number of earthquakes here in the Canaries, but no earthquakes in between. And that's very strong evidence that there's a disconnect. There's no real connection between the Atlas Mountains and the Canaries. But if you look up here, you see the plate boundary is marked with loads of earthquakes, and these feed all the way to the triple junction that hosts the Azores. So the Azores, furthermore, they sit on a lot of fractures, and this is why the Azore Islands are very elongate. They're strung out along these fractures, and I'm showing in the right-hand side the other map I showed earlier with all the fractures close to the mid-ocean ridge. We have a lot of these fractures, and the Azores exploit them. The Canaries are more blobby, generally speaking. They don't have so many fractures. They have to push the way through themselves. They cannot exploit fractures so easily. So let me quickly summarize before we move on to a slightly different topic. And here we have the oceans of the world, and a really mature ocean has three types of volcanoes: rifts, spreading zones; plumes, where material rises up anomalously; and subduction, where ocean crust is subducted into the mantle again. And the Atlantic is just about starting to have subduction at the edges, so the Atlantic is just about coming of age. As oceans go, the Atlantic is very young. But a lecture about the Atlantic wouldn't be complete without talking a little bit about Atlantis. So you find these type of newspaper cuttings, and they go through, well, many decades. This is a slightly older one, the search for the long-lost continent underneath the ocean. And well, Atlantis is not just a beautiful myth. I actually think there's some substance to this. So let me go into that a little more. Where does the concept come from? Well, it's the Greeks that called the sea outside the Pillars of Hercules, they called it Atlantic, the Atlantic Sea, and I'm giving you a few sources here. This goes back to about the 6th and 5th century BC, so the concept of the Atlantic Ocean is pretty old, and it's the sea outside Gibraltar. We just came through Gibraltar this morning, very early at about 6 in the morning or 6:30, I think, and there we're now out in the ocean again. And in ancient Greece, Plato was the person who wrote about the demise of Atlantis. And well, there has been discussion ever since. Was it real? Was it fictional? Did he take some artistic liberty or not? And people have been looking for Atlantis ever since. You will find many different maps if you go on Google and search for Atlantis. There's a wealth of information. So I'd like this map here in the lower left in particular. So let me show that to you. So here it is, and there Atlantis seems to have a big volcano in the middle, and there's America, and there is Africa and Europe. As you'll quickly realize, the north is actually at the bottom of the map, and south is to the top. So this is a map that was flipped around back in the days. People had different conventions at times. And in this map, this is a little younger. This is actually from the 1920s. And this author here puts Atlantis here in the middle of the Atlantic, actually pretty much where the Azores are. Sorry, I'm struggling to keep it still. Here we are. So and many other authors took inspiration from this. Most maps that you find online, these are all pretty young maps, and many of them are fictional. They put Atlantis actually where the Azores are, in the triple junction between the 3 geological plates. And, well, Plato says that once Atlantis sank into the ocean, all that was left was the peaks of the highest mountains. And, well, if you go to the Azores, there's this rather beautiful volcano, which is called Pico. So, and it sticks out, and this is very tempting to assume that this might be this large volcano that was in the center of Atlantis. But we nowadays know that Pico Island is not connected to a big continent underneath. So this is a bit problematic geologically speaking. And then Plato, he describes that this was a very complicated architecture which had circles of water and channels and things like that. So on the left is an artist's impression of how the main settlement on Atlantis could have looked like. And then, of course, nowadays, many artists like to think about the drowned, beautiful world of Atlantis. So here's a few impressions on the right-hand side. Every now and then, you find newspaper headlines like this: Atlantis found, clear, obvious evidence, and Plato's lost city sunk near Britain. So, and there is what they look at, the Rockwall Trough. This is a plateau, an elevated plateau, and of course it sparks wonderful imaginations about that Atlantis could actually be just offshore Britain. So that would imply we can go there and explore it. But I have to disappoint the Express a little bit. The issue is that when you look at Iceland, the Iceland plume here it is, and the Iceland plume is going for quite some time, several tens of millions of years, and before the Atlantic spread to the extent we have it today, there were several lava plateaus forming, and one of this is the Faroe and the Rockall lava plateau, which is here. So what these authors here consider to be Atlantis is nothing but old Icelandic basalt rock that seems to be elevated. So no show for the Express, but there is something out there, and this is Doggerland. Maybe you heard of Doggerland. This was an area in between nowadays the British Isles. Let me show you here. Here's the British Isles in dark green, and Scandinavia. And this was land that was above ground back in the last ice age. Most of the water was locked in the glaciers, and therefore the ocean level was actually lower, and the land in between continental Europe and the British Isles was above sea level. This is how people actually managed to go to the British Isles. They walked there, believe it or not. So, and there's good evidence for this, and I'll show you this wonderful mammoth skeleton that was brought up by fishermen from that area, from the Dogger Bank. So mammoths did walk that part of the world. So this was clearly above the water. Otherwise, well, I don't think mammoths were good swimmers. So from that point of view, there was a sunken world. And I think Plato heard about that. And he combined this with the tragic story of Santorini, where the Minoan culture was exposed to a big volcanic eruption. And he put these two things together. So he considered this sunken world beyond the Pillars of Hercules, which is certainly true for Doggerland, and he combined it with the volcano experience. And therefore, he took a lot of artistic liberty, and he described this wonderful story of Atlantis, of a sunk area. And let me show you a few more images here. Oops. Let me bring you back. So Doggerland eventually drowned after the glaciers melted, the water was rising, and well, eventually the island, or the British Isles, were separated from the continent of Europe, and we still have the Dogger Bank. There's still an area in the central part in the North Sea that is somewhat elevated. And glaciologists are really keen on this. Let me give you an impression here. So on the right-hand side, we have Doggerland and the connected continents during the last major ice age. And then with time, this sank. So there's a timeline here. And some 6,000 years prior to our time reckoning, Doggerland was gone. But humans were, of course, around, and this is how people migrated through the British Isles at the time. So I'd like to close with a few words about the treasures of the Atlantic, and you all heard about Treasure Island and various other things. And well, there could be treasure in Atlantis. I haven't explored this, but I'd like to stress that there is a lot of wealth in the Atlantic if we were able to retrieve it. There's a lot of resources, and there are a lot of modern researchers going into this. At these black smokers in the crest of the mid-Atlantic ridge, we actually have a lot of mineral precipitation, and these black clouds, they're actually tiny little microlites of metal-rich minerals, and they get deposited there, and they are often making a lot of sulfites. And here's a sulfite sample with my finger on it. So this is how they look like. They make typical copper and iron minerals that are bound by sulfur, and this is something we will find extremely useful. There's a lot of copper produced there, and copper is one of the elements we will need a lot of, not just for electronics, but also, let me give you this impression here. If we are converting our car and traffic fleet to electrical vehicles, we need huge amounts of more copper in the future. So a conventional car is shown here on the left. If we think about electric buses running in the future, our copper consumption will skyrocket. We will need a lot more copper. The good news is there is a lot of copper under the ocean. Should we get it or not? That's an ethical discussion that we need to have, but there is no shortage of copper if we are prepared to get it. So this is how the copper forms. We have these large smokers, as we call them, but I stress once more, this is not smoke. This is actually chemical precipitation. And, oops, here we are. We find that there's mounds of these sulfides forming, and there we have chimneys of materials where they bake together. So if you find one of those mounds, then you are, well, you have a lucky strike. And around these mounds, there's a lot of life as well, very bizarre landscapes on the oceans, but very mineral rich. And this is a hydrothermal formation of ore. And how does it work? Well, this is from one of my geochemistry lecture. I don't give you a lot of chemistry, don't worry. But here we have ocean water creeping down into the substrate. There, the ocean water heats up from the magma. And once you have hot solutions, it leaches elements from the rock. Well, we all know warm water is better for cleaning things than cold water. So if you have warm water, it also takes things out of the rocks. And once the hot, heated water rises up again, it meets the cold ocean floor. That's usually basic in chemistry, while these fluids are acidic, and then they bring a lot of these metals and deposit them on the ocean floor. There's one exception, or actually two exceptions. Two of the elements, they love to stay in the ocean water that are not precipitated right on the spot, and this is manganese and cobalt. And they are also very important for battery technology. And they get transported away from the ocean ridge because they are dissolved in the ocean water. And they form crusts like this. This is a small specimen with a manganese and cobalt crust. It's the black crust on top of that rock. So, why is this important? Well, we need cobalt and manganese for our batteries as well. Cobalt is currently coming with almost 70% from one country, the Democratic Republic of Congo. The mining conditions are not very pleasant there, and there's a lot of miners dying, a lot of actually artisanal mining that includes, for example, well, whole families mining, i.e. child labor. So there is huge efforts now in Europe, certainly, to find cobalt elsewhere. Elon Musk, he is a smart chap. He knows that there is a lot of cobalt in meteorites and asteroids. This is why he's pushing a lot for space mining and space exploration. But there's also a lot of cobalt on the ocean floor, I would like to point out, and it precipitates away from the actual ridges, and it comes in these crusts. And there is actually little lumps of rocks that get encrusted all over the ocean floor, and there's real fields of little manganese and cobalt nodules. And here's a section through some of them. So here's a few samples that we retrieved. And there you see regular rocks in the core and crusts of manganese and cobalt, the black material surrounding them. So these fields are vast. The big challenge is now, how do we get them up? And how do we get them up without destroying the ocean floor to a degree that life on the ocean floor suffers? The EU has just funded large projects. These are not realities, these are artists' impressions. There's ideas about hoovering them up, for example. There's ideas about having these diggers that would actually operate on the ocean floor, and they would be remotely controlled. We wouldn't send people down there, and they could actually bring some of this material up. So there could be a future for deep sea mining, and we would probably have to do it in big, widely dispersed areas because we would not want to compromise life in one particular spot. So you would have to almost build areas where we do some mining in a small area with loads of unchanged habitat for ocean creatures surrounding them. Maybe that's a discussion. And there is, of course, all sorts of life down there. The life is getting very small. It's not the big sea monsters of Jules Verne. It's actually tiny little creatures that we expect down there rather than big ones. And as Greenpeace rightly points out, there is, of course, something a little odd, something a little ironic, that our wish for clean energy and for driving renewable energy at the surface of our planet might cause the destruction of the environment at the ocean floor. So there we have a little bit of thinking to do and see that we get that right. So hopefully we'll find good solutions for this. I'd like to close at the very end with giving credit to this gentleman, Jules Verne again, because he actually saw this long before submarine ocean research. He knew there was volcanoes down there. He knew that there was a lot of resources down there. Captain Nemo, he was mining submarine, and he also realized we will struggle with submarine life forms. Only the life forms we really have to be worried about are tiny and not as big as Jules Verne pictured them. Thank you very much.